Okay, so this video will be how to figure out what type of intermolecular forces are present in a substance. Okay, now, anyway, so my examples start here at the bottom. So right here is LIF. So if we look at LIF, what we're going to do is we're going to see that lithium is a metal. And if the first element is a metal, it's going to be ionic. So metal, nonmetal, ionic. All right, that's a pretty simple one. All right, let's do another one here. Okay, O3. All right, well, O3 is not ionic. It is a covalent. And so the thing is, you got to know whether it's polar or nonpolar. So what you got to do first is you have to draw it. So you would go oxygen, oxygen, oxygen. You would find out when you draw the Lewis structure, it ends up looking like this right here. And so O3, there's three things, but there's three domains, so it is bent. And if you remember that bent ones are always polar. So bent is always polar. Now, does this have hydrogen bonding? Well, of course not, because it doesn't have a hydrogen in it, because you got to make a hydrogen sandwich. So the only type of force present in this one, besides dispersion forces, is because everything has dispersion forces, would be dipole, dipole. Okay, and it also has dispersion forces. Everything has London dispersion forces no matter what. Okay, let's go on to the next one here. All right, so CH4. Like I said, if you can't tell right away, you might have to draw it. It's not ionic, there's no metal. So you would draw it and you would end up getting this right here. So CH4. All right, and so it's covalent. Okay, but it's non-polar because it's tetrahedral and it's symmetrical. This is non-polar. Therefore, the only forces that this thing has between itself and another molecule would be London dispersion forces. All right? Okay, NH3, so you would draw that. Nitrogen, hydrogen, hydrogen, hydrogen. Yeah, you got to draw them if they're covalent. And so nitrogen is not a metal, so you know it's got covalent bonds. You end up getting that, and you see that definitely is going to be trigonal pyramidal. That makes it, so I'll just write that, trigonal pyramidal. Okay, and trigonal pyramidals, if you remember, are always polar. Now, can this one hydrogen bond with itself? Well, it has a hydrogen in it bonded to a nitrogen. So if there was another ammonia, so here's this one right here, let's say. All right, if another ammonia came along, you could have three hydrogens here. I can draw, right? And then the nitrogen would be up here. Now this one, what would happen? There would be an attraction right here. Now, does that make a hydrogen sandwich between FO or Ns? Nitrogen, hydrogen, nitrogen? Yes, it does. So this one has hydrogen bonding in it. Okay? So it has hydrogen bonding. Also, it has dispersion forces. Okay? It has both. Okay? So everything has London dispersion forces, no matter what. All right? Okay. Oops, I went to the wrong page there. Let's see, I gotta go to the right page here. Okay, CO2. All right, so you would say, well, it's not a metal, so it's definitely got covalent bonds. You would draw it, it looks something like this. Okay, now it's a linear molecule, but it's symmetrical. The dipoles would cancel out. And so what would end up happening is it's going to be a covalently bonded substance, but it's non-polar. Okay, because it's linear and it's symmetrical. So this one only has London dispersion forces. Okay, HCO2. And this is the same thing that I did on the other one. I meant to make it H2CO, not H2CO2. That's a typing error. So you would have carbon, hydrogen, hydrogen, double bonded oxygen. All right, so now this one's kind of a tricky one. All right, so now you know it's covalently bonded. All right, but it's trigonal planar, but it's not symmetrical, so it's polar. Then the question comes, can it hydrogen bond or does it just have dipole-dipole? So let's look at how this would hydrogen bond with another one, if it would. Okay, maybe it won't. So let's see. So this oxygen end, oxygen's more electronegative, so this end's going to be negative. So if we put a hydrogen over here, which might be slightly positive, but ever so slightly because of the carbon bond. So the hydrogen end would have to go here. Now we would draw that. Let's see, hydrogen, hydrogen, double bonded oxygen. So there would be some attraction right here. But is that a hydrogen bond or not? So the hydrogen has to be sandwiched in between F, O, or N. So is it sandwiched in between an F, O, or N? Well, oxygen, hydrogen, carbon. No, so no sandwich. Okay, so because there's no sandwich, all right, then it's not a hydrogen bond. So this one is a dipole-dipole. It's a polar molecule, but there's no hydrogen sandwich. So it doesn't contain hydrogen bonding. Okay, HF. Okay, so non-metal, non-metal. So we know it's not ionic. So we'll draw it, which is a pretty easy one to draw. Well, that's linear. Okay, so linear ones, if the two things aren't the same, then you're going to say that it's polar. Now, can it hydrogen bond? So let's see. If we had another HF come along, HF, there would be an attraction right here between them. Does that make a hydrogen sandwich between F, O, or N? So hydrogen, there's a fluorine, hydrogen, fluorine. Yes, so that does. This one is an example of hydrogen bonding. So this one, the attraction between molecules would be hydrogen bonds. Okay, so I guess that's it for that video there. I hope that helped.